So I've heard about compression making files smaller, but how does it actually work? Why not just use a simple, fixed code for every single character?
That's a great question, and it gets right to the heart of the matter. Using a fixed number of bits for every character is simple, for sure, but it's often really inefficient. It's like giving every word the same amount of space, whether that word is A or anti-disestablishmentarianism. It works, but you end up wasting a ton of space, especially when some characters show up way more often than others.
And what's really interesting is that in this sample, you can see A and T are way more common. So a much better approach would be to give these frequent characters shorter codes and the less frequent ones longer codes. This is the core idea of variable length coding.
Okay, that makes sense for saving space. But if the codes all have different lengths, how can you read a long string of bits without getting completely confused? How do you avoid any ambiguity?
The solution is just so elegant. We use what's called a prefix-free code. So the crucial point here is that no character's code is the beginning of any other character's code. Once you've read a valid code, you know for sure that a character is ended. There's no guesswork.
And this illustrates it perfectly. Let's say A is 0 and T is 11. We can read this stream of bits without any problems. The first unique code is 11. That has to be a T. The next is 0, that's an A. Then another 0, another A, and so on. There's just no confusion.
So how do we actually create the best possible prefix-free code for a given file?
Okay, let's dive into this. We use a really clever method that builds a special binary tree from the bottom up, and it does it based on those character frequencies using what's known as a greedy algorithm.
A greedy algorithm? What does that even mean in this context? Well, it means that at each and every step, the algorithm makes the choice that seems best at that exact moment, without worrying about what might happen down the line.
It means we always pick the two characters or combined groups with the absolute lowest frequencies, and we merge them. Let's move to the next slide, and you'll see exactly how this builds the tree, step by step.
Okay, so we start with our 4 characters. The greedy choice here is to combine C and G, right? Their frequencies are the lowest. Then, we combine that new node with T, because that new node and T now have the lowest frequencies. And finally, we merge the last 2 nodes left to create the root of the tree.
And this is the result. To get the code for any character, you just trace the path from the root. So a left turn is a 0, a right turn is a 1. For example, the path to G is right, then left, then right again. So its code is 101. It's that simple.
By repeatedly making this simple, greedy choice, Huffman's algorithm guarantees an optimal prefix-free code. It just pushes the least common characters deeper and deeper into the tree, which naturally gives them longer codes. It's brilliant.
This is very clever, but it seems like you have to read the entire file once just to count the frequencies, and then a second time to actually compress it. What if you can't do that? What if it's like a live stream?
An excellent point. For that exact scenario, a variation called adaptive Huffman coding exists. It cleverly builds and actually modifies the tree as it processes the data, which allows for compression in just one single pass.
So the crucial takeaway here is that Huffman coding is this powerful and elegant solution to data compression. It uses frequency to assign shorter codes to common characters in a provably optimal and, importantly, unambiguous way.
It's just fascinating how this simple greedy algorithm produces a perfect overall result. It really makes you wonder, where else does that principle apply?
We hope this explainer shed some light on the magic behind data compression. If it did, well, please consider liking and subscribing to see more. Thanks for watching.